Hello. I think we're going to get started shortly. I get the big room, so it gets to seem very, very empty as people go to interesting talks. All right, this is my talk about the I/O monad and about effect systems and about how all of that stuff works in Scala. So if you're like me, you've probably said to yourself at some point in the past something like this, which is that the I/O monad is just garbage. Like it's just this thing that Haskell forces us to do, mostly because Philip Wadler is like mean like that, and things. But it's really like nothing could be further from the truth. Okay, and the I/O monad is really about effects. It's really about effects. It's about controlling effects. It's about making them work better for you in this way that's very, very difficult to do if you don't have something like the I/O monad. So it's taken me a really long time to learn this, and a lot of very painful lessons along the way. So hopefully this talk will allow you to kind of short-circuit that process just a little bit, and maybe get a chance to see how this can work for you and make some of the things that you are trying to express easier to express, not harder, not verbose, and not just trying to please Phil Wadler. So effects. What is an effect? Well, an effect is basically anything you can't just do twice, right? So like writing to a database, reading from standard input, changing state, any of these things, right? Like all of these are things that you really have to do it once. You can't do it twice unless like you intend to do it twice, and in which case good, but do it exactly twice, not once, not 3 times. And you really have to do it exactly at the moment that you say you want to do it, okay? These are what effects are. They require very, very, very careful control. They're also very hard to test. Okay? We have these whole like test suites and tools for mocking and like these techniques for dependency injection and like splitting up services and stuff like that to try to make the things that have effects easier to reason about, easier to put together, easier to write tests about. Because honestly, like the way to write quality software is just write more tests. It's not complicated. It's just getting to that point is very hard, and effects make it harder. Effects also make concurrency very, very, very hard. So if you think about what the hardest problems when you're dealing with multi-threaded or parallel systems is really just like I've got some state or I've got some like sort of shared resource that I'm operating on in this effectful way, and I have to somehow coordinate and linearize that. That's very, very hard. But at the same time, concurrency without effects is almost useless. Like you have folding at home, basically. That's like the only thing you can do with concurrency if you don't have effects. So that's not really helpful, right? So it's kind of like the best of times and the worst of times, right? Like you have to have effects to make concurrency worthwhile, but they make it very, very, very hard. They also make refactoring hard. Okay? This is one of those things that I think people who are newer to functional programming don't actually think about all that much. But refactoring is actually just, is difficult almost entirely because effects are something that can happen at any time in most languages. So what do I mean by that? Well, here's an example. foo42 plus foo42. Okay? We look at this and we're like, well, there's some duplication in this expression. It would be really nice to kind of factor it out and have, val x equals foo42, x plus x, right? But we can't do this. And we can't do this because foo could be something complicated that, does something other than just returning an integer, right? We don't really know. We have actually no way of knowing from the outside. We're just, Scala allows us to do whatever we want here. So for example, like maybe foo is actually add to gauge, right? And if we add to gauge once rather than twice, that changes the meaning of our program, right? Our gauge doesn't increment multiple times. So that's kind of a significant thing. So effects are kind of hard in this way. And I would say that like because of all of these properties, right, effects should be controlled very, very, very carefully. We should try to build constructions and build abstractions in our program that allow us to take very, very great care around our effects and sequence them exactly the way we want and only the way we want, and avoid these sorts of problems ideally. And the standard way of doing this in languages without linear typing, without roles and things like that, is a monad, right? So this is the IO monad. We could, if we redefine the add to gauge function from our previous example, we can see how this construct actually allows us to avoid the problem we had on the previous slide. So the program sort of to the left is the sort of, we've got the duplicated add to gauge thing, and we had to put it inside a for comprehension, but it's still basically the same thing, right? And then on the right, we have this sort of val x equals add to gauge, and then we just sequence x twice in the for comprehension. And the beautiful thing is that these two programs are the same. Right? There's actually no difference between these two programs. And this is a fundamental property that the IO monad gives us surrounding effects. Right? It takes effects, which are this sort of scary thing that you want to control, that can do these really kind of uncontrolled things to your program, to your state, and it turns them into something that we have really, really tight power over. We have referential transparency, and we can do a lot of really interesting things. So I said that it's not just about effects themselves, it's also about concurrency. And we can see that if we look at basically the sorts of things that we are trying to do most of the time with concurrency, right? Because most of the time we're trying to do, or at least the complicated things that we're trying to do, is build graphs that kind of look like this, right? Where, from a control flow sense, where we start off at some like single point A, and then we sort of fork off, and we do like some tasks in parallel, and then we come back together at some shared point, and we mediate between the two sides, and conclude with an answer, right? Most reasonably interesting concurrent programs, concurrent algorithms have this kind of structure, perhaps with larger order. But this is basically the idea, right? And we actually struggle. We struggle most of the time to build these things because we don't really, don't really have a first-class representation of this. We don't really have control over the A's and B's and C's and et cetera, et cetera. It's actually very difficult to put this together. And we have frameworks that have sprung up that have tried to give imperative sort of affect uncontrolled systems the ability to represent this. Actor libraries being the most notable example. And it's still really, really, really hard to find your way through this. Whereas if you have a controlled abstraction for effects, right? If you focus on the effects, then figuring out the composition, which is to say like where your arrows go, is actually pretty easy. So for example, here's a representation of this graph using the FS2 library, which is a framework for controlling streaming effects in a purely functional way. And you see what we can do is we can just describe each point in this computation, each effect in individuality, and then we can describe how they compose together. And that hard bit, right, the hard bit at the bottom where things come back together at the end, is just a single point in this graph, right? A single point where we say, D merge F, put them together, and now we have G. So doing this sort of stuff is really, really powerful, not just from the standpoint of making our code easier to reason about and easier to test, and like all of those are good reasons in and of themselves to do it, but it also solves basically all of the meaningful problems with concurrency by circumventing them altogether, making it easy to talk about composition. So the IO monad is kind of the basis of this stuff. It's the basis of this talk. And what it does is it allows you to safely manipulate effects. It allows you to safely control effects. And you do this by building a description of your program to be run. You don't actually run the program, you build a description of it. And this is a really important distinction, right? So when you say print line foo semicolon print line, right, you're not building a description of your program, at least not a really useful one, right? Like technically it's a description, but the only one who can look at it is the JVM. And by that point, it's way too late for you to do anything about it. The IO monad lets you build a description of your program that you can manipulate, right? And this is where the really valuable thing is. And if any of you have any experience in the Lisp community, this should sound really familiar, right? It turns out that code as data is actually a really powerful concept. And the IO monad is one way of doing this, right? It's one way of doing it in languages that are not homoiconic. What this does, by building these descriptions, we separate the composition point from the definition, right? So if we declare what it means to perform a particular effect, and we do that in sort of an abstract descriptive way, we can separate that out from the part of the code that declares how we put those effects together. And this is what gives us those concurrency properties, right? It gives us the ability to represent other things that you don't traditionally think about when you think of pure functional programming, like dynamic scaling, right? If you think of back pressure and sort of dynamic rescaling and like allocation and pool management and things like that, all of these are real problems that you have when you get into systems programming at scale. They're actually really, really, really easy when you have a powerful effect abstraction, because all we're talking about when we talk about scaling is just how your effects are composed together, how they're scheduled, how they're going to be run. And if you have an abstract description of your effects that's not in flight and out of your control, then changing this stuff is really, really easy. So the first question that you should generally ask when you're looking at something like the IO monad is, what is about this monad part? Like, why is it a monad? IO certainly doesn't look anything like option or list, so why are we doing monad-y things? Well, it comes from the fact that program actions have to be sequentialized, right? You really have to do, if you say, print line hello, print line world, you really mean hello world. You don't mean world hello, right? And you need that to be definitional. You need that to be like, in the way that you compose those two effects together, it's always in a sequence. And monads are the essence of sequencing. This is actually the definition of a monad, right? Like, monads do nothing other than put things together in a particular order. So if we want to say A happens before B, we really need a monad to say that. And this is why the IO monad is a monad. And critically, this was Phil Wadler's insight. Right? This is why we use monads to manage effects in the first place. It's because Phil Wadler realized that this construct in category theory could be used to represent sequentiality in a functional programming language, in his case, Haskell. And that's how we got on this whole train in the first place, 27 years ago or whatever it was. And we can see why this is if we just look at the definition of monad. So here's the monad type class. You can sort of quibble about the names of these functions, right? I called them pure and flat map. Scala Z would call them like point and bind. Haskell uses return. Like, the names actually don't matter, right? We've got one function for putting a value into a monad, and then another function for putting two monads together. That's what a monad is. And we can see, just by looking at the second function, at the type of the second function, that this has to be sequential. Okay? It has to be sequential. The FA has to happen before FB. How do we know that? Because of the A, right? We know it because of the A. So the FB that gets returned from flatmap, the only place it can come from is the function that goes from A to FB. But the only way the function can operate and give us an FB is if we give it an A, right? Not an F of A, an A. Now, where can that A come from? Well, there's only one answer. It comes from the FA. Right? That's literally the only place in the whole universe that we could get this A if we don't cheat and use null or exceptions or something else that doesn't make sense, right? So we know, we in fact have a proof by the way this function is defined, by the type signature, that monads give us sequentiality every single time. FA has to happen before FB. FB cannot even exist until FA has run. That's really, really, really fundamental and important. And these sorts of arguments are what we're talking about when we say that we argue things by parametricity, right? That term means exactly what we just did. And this is a very, very powerful technique. When you're working with pure functional programs and you're sort of controlling your effects and doing things in a very sound and principled fashion, you can make these arguments a lot. And you can learn very, very rich properties about your program just by looking at the types involved and make these sorts of arguments all the time. It's a really, really powerful technique. So we know that monads are sequential, and the IO monad is basically what we're going to be using. And this is what it looks like in Haskell. Okay? So in Haskell, every program is an IO of unit. The sort of paren is how Haskell writes unit. And every program is essentially going to come back into this, right? You always have to run your program in IO. That's basically the whole point. And you hand your IO instance off to the Haskell runtime, and that's the end of your program, right? Your world is over. The runtime will just take care of things from there. So in Haskell, all roads lead to IO, right? Like everything comes back to IO in the end, which makes sense, right? Because the point of running programs is ultimately to perform effects, right? Like, what even is it if your program doesn't perform any effects? Like the box is getting warm. Like you actually have nothing else other than that. So all roads lead to I/O. And in Haskell, furthermore, all incoming roads, things that come into your language, i.e. FFIs, those are also wrapped up in I/O. So if you're in Haskell and you want to talk to something that's in C, or you want to get something over the network or something like that, you're going to end up, like, it's going to be handed to you already wrapped up in I/O. So you're really forced to it, right? And you can't construct an I/O in any way in user space manually, except by using return, which is the way that you lift a pure value into I/O, right? So you're not actually building something that captures effects, because the effects are already captured for you, okay? So Haskell is sort of taking care of all of this stuff. Additionally, whenever you work with concurrency, which, I mean, we're going to keep coming back to this as a really, really important thing in effect systems, it's all going to be managed inside of I/O, more or less, right? And what this is effectively getting down to is the fact that Haskell's runtime is actually a very, very high-level system, okay? It manages effects for us. It sort of puts things into I/O. It's going to run I/O for us at the end of the world. It insulates us from a lot of the details of low-level threading by using green threads, which are something that if you're familiar with like dynamic languages like Ruby or Python or like Erlang or something like that, like you know that this is a relatively high-level runtime construct. Haskell does all of this stuff for us. And so because everything is relatively high level, their I/O monad can be very, very simple, right? Where like we literally only have the ability to put a value into I/O and then bind with it. We don't actually have the ability to wrap up effects or like run it or do anything crazy, right? Because the Haskell runtime takes care of all of that for us. But we are not Haskell, right? We're working in Scala. And in Scala, the things are a little bit different, right? So here's a main function in Scala. And the main function in Scala just like returns unit, right? Like we really don't have anything. And we can't say anything, like if we try to make a parametricity argument about this function, like literally the only thing we can say is, well, it performs a side effect. And that's it, right? Like we can't say anything about it because unit is so completely opaque. I guess it's good that we don't have reliable screens. So we're kind of in this state where we don't really know anything, that the platform isn't really going to help us out in terms of getting along with this. And furthermore, like, while the platform doesn't help us out at the endpoint of our I/O, it similarly doesn't help us out when we're creating them, right? So there's no FFI between Java and Scala, right? So even if Scala really forced you to make sure that your effects were precisely controlled, Java certainly doesn't. And we can always call a Java function just sort of natively in the middle of our Scala code that pretends to return an integer, but actually, I don't know, talks to the database, right? This is basically the entire JDBC API. That's not going to be wrapped up in I/O. Java doesn't know anything about I/O. And so we're going to have to find some way of taking care of that by ourselves. We can run any effects we want at any time. And in fact, because the evaluation is eager, then any effects that we try to describe are running. Like, it's like this terrible ephemeral thing, right? You say print line, and before the n is even out of your mouth, it's printing, and you can't do anything about it. So we have to find some way of sort of calming that down. Otherwise, there's no way that we're going to be able to solve this problem in a meaningful way, right? We have to get in between the description of the effect and the actual running of it. And furthermore, Scala has very low-level concurrency primitives. So I'm not even talking about actors here, right? I'm talking about the fact that we're on the JVM. And we have native threads. We have locks. We have callbacks that we have to manage because our threads are like this really expensive thing that we can't really do anything with. We've got all of this stuff. We have to deal with all of that very, very, very explicitly. So the JVM is a much more low-level runtime than GHC's runtime. That doesn't make it worse. It just means it's much more low level. And fundamentally, the I/O monad is all about the runtime. It's all about controlling the runtime of your program. So we're going to have to do something very different than we did in Haskell in order to make this work, right? So Scala runs on the JVM. It has native threads. It has explicit asynchronous I/O, right? So when you use like the JavaX NIO package or something like that, you actually have to like explicitly pass around callbacks and like ghetto Node.js yourself. And there's really no other way to do it other than blocking threads, but you can't block threads and like all of that. It's terrible. I don't know. It's like managing that is a pain, and it's really part of operating on the JVM at scale. We also don't have tail call elimination, right? This is another runtime concern, but it really fundamentally affects what we have to do here. So you've probably heard a lot about tail call elimination, right? It's like this thing, sort of this magic white whale that we would love to have in the JVM that apparently all of the JVM authors would love to have in the JVM, but we just can't have because of some decision that was made at Sun Microsystems back in the early 90s. And it's this really important thing, and especially for something like I/O, where effectively, like, remember, we want to encourage people to write their whole program inside of I/O. Like, at the end of the world, right, like, all of your stuff is going to come down and be composed inside of the I/O monad. So you're probably writing a real program that, I don't know, runs for a long time, maybe forever, because most interesting programs actually run forever. So, like, we really can't take anything other than constant stack space. Like, we can't blow the stack because the JVM isn't going to help us with this. So whatever we do with I/O in Scala, it's going to have to solve this problem, right? As well as several others. So these are all concerns that we have to worry about that Haskell just doesn't. But there are some things that are the same, right? So the I/O monad in Scala is still going to be a monad, right? The argument that we just made about sequentiality and parametricity, like, all of that still holds. It's going to provide stack safety for us, and it's going to provide some different evaluation models, right? So Haskell's I/O, right, really only cares about one evaluation model, which is the evaluation of Haskell itself. And, you know, all of the differences between callbacks and sequentiality, that just gets handled by the runtime. For us, we need, at a minimum, 3 evaluation modes, right? So we need strictness. Okay, so let's say we already have a value in our hands. We want to put it into the I/O monad, and we don't want to pay the penalty of, like, wrapping it up in a function, you know, thunking that, or, like, you know, putting it inside of a callback or anything crazy like that. We really don't want to pay those penalties because that's very expensive on the JVM. Allocations are not cheap. So when we're dealing with values that are already pure, that are already in our hand, we should be able to put those in I/O and not really pay a penalty. But we also need a lazy evaluation model, right? A synchronous, lazy evaluation model, because we need to be able to capture effects like printline, for example. And we need to be able to say printline and not have it start printing before we have a chance to control it. So this is where the laziness comes in. But we also need asynchronicity. This is probably the most surprising thing about I/O monads in Scala if you're coming from a language like Haskell, because in Haskell you don't really think about being asynchronous, right? Because you have green threads, right? Why would you care? The runtime's just going to do it all for you. But in Scala, we have to care about this. We have to care about explicit callbacks. And, like, callback management is a huge pain. And it's really, like, a fundamentally different, you know, runtime model for your program. Whatever we do with an I/O monad in Scala, it's going to have to take care of this for us. Because, again, we don't want to think about these things. They're really hard. And asynchronous effects are incredibly important when you want to write systems at scale. All of this is going to have to be represented by effect capturing constructors, okay? So this, again, is like a really weird sounding sentence, right? We have to be able to construct I/O capturing effects. But again, like, that's the world we live in. We're on the JVM, we're on Scala, we have to be able to do these things, and we have to have constructors for all of these cases that, you know, either lift a pure value or capture, like, a lazy synchronous effect or capture a callback-based API. Like, all of those different things, we have to be able to build I/O out of those things. So what options do we have in Scala for, you know, what candidates are there for perhaps meeting these requirements? Well, one really obvious one that everyone should be thinking about is Future, right? Like, Future is baked into the standard library. We've all used it at some point. Some of us use it a lot. And it's there, right? It's sort of the incumbent solution. But it has a ton of problems with it when you're thinking about it as an I/O monad, right? It's very useful for doing some things, but as an I/O monad, it kind of falls short. And you can see this immediately because it runs actions eagerly by default, okay? If you construct a future that wraps around printline, it's printing. And you can change this by messing around with your execution context, but by default, it's still running eagerly. And it's actually very difficult for you to override this. And even if you do override it, if you pass through sort of some API, that API could actually change the future out from underneath you and decide to run it anyway. So ultimately, you just have to assume that it's running, because that's probably what's happening. And that's a real problem. And, you know, equivalent to running immediately, it also memoizes its results, right? So we can only run it a single time. And once we've run it, we have to be very careful that we don't leak memory. So I have had real in-production bugs that are caused by building some large object inside of a future that I wasn't getting to yet or wasn't actually planning on getting to, and the future just held a reference to it forever, and like I ran out of memory on my JVM. That was really, really unpleasant. But this eager running thing is really, really, really a problem. It's really like fundamentally the issue that prevents future from being useful as an I/O monad, and we can see it with an example like this, right? So here's our add to gauge thing, right? Like this was the thing that motivated the whole talk, is like being able to do this, have val x equals add to gauge, and then make sure that the gauge gets added twice. But if you do this with future, we're only adding to the gauge once, because that future that we constructed in x, it's only going to run a single time. So future is just not an appropriate tool to apply to effect management. It's just not going to work. So we have to do something else, right? Future also, just to keep piling on, right? Like future also doesn't actually encapsulate asynchronicity particularly well, right? Which is surprising, right? Because that's literally the whole point of the abstraction. But like ultimately, I'm going to say that promise is a pretty leaky abstraction, right? You create a promise, it doesn't have a future attached to it, you can do stuff with it, or maybe not, who knows? You create a future, it's over here, completely disconnected, you have no way of knowing whether it's connected to this promise or not. Like maybe the promise has been fulfilled, maybe it hasn't, maybe you took the promise and put it over there and serialized it out to disk because you're using Spark. Like, I don't know, like random stuff is happening, and it's really difficult to keep all of this under control, right? So promise is kind of a cool idea, but it's like just completely divorced from the thing that it's trying to control, and that makes it very, very difficult to keep a handle on in practice. Future also, surprisingly, rewrites exceptions. So when you throw an exception inside of a future, right, or you have an effect which throws an exception, which is equivalent, future will sometimes actually rewrite that into a wrapped exception. And in practice, like there's no theoretical problem with that, to be clear, right? There's nothing in like math that tells us that that's wrong. But practically, it is really frickin' annoying. Like it's really annoying to deal with the fact that your exceptions might be wrapped, might be unwrapped, you have to look, you're not really sure, and you have to worry about all of these types everywhere that you're trying to get exceptions back out of future. There are like currently active bugs on Quasar because of this thing right here, and it's really, really frustrating to pin down. So future is just not an option, right? We really can't do it. So we have to keep looking. Like what else might there be? Well, in Scala Z7, there is actually a thing called I/O. So Scala Z7 I/O. And Scala Z7 I/O is like this ancient tome from the Stone Ages when like we didn't have asynchronous programming, I guess. I don't know. Because I/O is really, really crude. It was basically ported directly from Haskell, and without taking into consideration the fact that Scala is not Haskell, and as a result, it's very, very limited. It doesn't support asynchronous programming at all, which is a huge, huge problem, because all of the interesting things that we do nowadays are asynchronous, because guess what? You can't handle like 1 million clients on a single box without being asynchronous. That's just not possible. So because it's not asynchronous, it encourages you to do terrible things like thread blocking. And it gives you this construct which very alluringly encourages you to block your threads and promises that it's OK. Spoiler alert, it is not OK. Do not use mvar in Scala Z7. It's bad. Even for people who know that these things are dangerous, it still leads you into this really unpleasant place. So this is probably my favorite pair of practical real-world type signatures of all time. And you can see immediately what is so bizarre about this, right? It's these two things right here. We have basically the same function. Like this is literally the same function, both in name and in deed, except one of them is synchronous, the other one is asynchronous, and we're using both I/O and future together. Good luck whoever's calling us, because you're going to have to sort out that whole mess. Like it's really confusing. This is real code. I actually touch this every day, and it's terrifying. So like this is what this leads you to, right? So Scala Z7 I/O is just not going to work. It only defines a lazy effect capturing constructor, right? Remember we said we needed 3 evaluation modes, strict, lazy, and async. Scala Z7 I/O only gives us lazy. And so it's very, very slow when you already have pure values and you're trying to wrap them up inside of I/O. You have to thunk. Additionally, and I haven't mentioned this before, it provides exactly 0 abstraction aside from the lift IO type class. Now, the lift IO type class is kind of this simple thing that basically just says, OK, I've got an IO of A. I can turn it into an F of A for some type constructor F, right? So this is useful if you're doing monad transformers or stuff like that. It basically just says that, OK, whatever my F is, it's bigger than IO. Like, it can have an IO inside of it, right? But this is the only abstraction that Scala Z7 IO gives us. It doesn't really describe what it means to be an effect. There's no laws here. Like, all of that stuff is important, and we're going to talk about it a little bit later. So Scala Z7 IO is not a good solution. What else is there? Well, Scala Z7, ironically, actually has 2 IO monads, and the second of which is one that basically everybody who uses Scala Z is going to use, right? And it's task. Okay? Anybody who's written any code with Scala Z uses task, and actually, like, a really astonishing amount of code in, like, the Scala ecosystem, period, runs in task at some point. It's really, like, astonishingly widespread. But it has some problems, not the least of which is the fact that the name is longer, which, believe it or not, has a material effect on my happiness because you're typing this thing 800 times a day. So that's kind of a pain. But it does support all of the constructors we want, right? So it has now and delay, async, and fail. So these are the 3 evaluation modes we talked about, plus the ability to suspend exceptions. All of that is good. Like, that seems to make a ton of sense, and it's basically what we want. But the implementation is bizarre. Like, it's really, really, really strange. Like, it's based on actors, and not even Akka actors. It's like Scala Z-ish actors, and it's like not really clear what it's doing, and it's like going to all of this effort to do something that really we could do much more simply. Like, it's a strange construction, and it very rightfully gets kind of a pretty bad rap from a number of people because of this implementation. And the implementation is horrible. But everybody uses it because it's so darn useful. It still doesn't have abstraction. And actually, it's actually taken a step back from I/O, where this lift I/O thing, right, that kind of sounded like it was almost a useful thing, we don't even have that for task. We have nothing. It's just task, right? It's purely concrete. So that's kind of a problem for a number of frameworks. And then finally, it gives us concurrency, which we've said is this important thing, but it gives it to us in a way which is full of bear traps and like lions and other terrible things that will jump out at us and ruin our programs, right? And any of you who have tried to write large systems that represent their concurrency using solely task and nothing else probably know what I'm talking about here, right? Because it actually kind of falls apart. And you just don't want to use the concurrency primitives that are attached to task. And I'm going to show you examples of this later. So what does task look like when we use it, right? Because like with all of its flaws and implementation and things like that, it's still, in terms of constructors and things like that, it still seems like it's pretty close to what we're looking for. And this is basically what a typical program is in task. We have a print line that we capture, like the effect of the print we capture in delay, and then we read a line from standard input. We tokenize that input into a bunch of names, and then we use this traverse function, which is like a totally generic function. It doesn't know anything about task. All it knows is monads. And the traverse function is going to go over every single name in our tokenized list and print them out, or produce a task that will print them out, rather. And then this whole thing is a program that we finally run at the end of the world. Okay? So we're presumably in our main function or something like that. We can call this unsafe perform sync function. So this is a pretty typical program. But you'll notice, like, this is all synchronous, right? Like, we're using delay. It's all lazy capturing of effects, right? We're not actually doing anything really interesting here, like talking to a network channel or like, suspending a callback off of a thread pool, that sort of thing. Like, all of these are much more real problems that we would have to tackle with task. So let's look at something more interesting. Here is a function that reads from an asynchronous socket channel. This is the Java 7 NIO library, because the Java 4 NIO library is too confusing and no one uses it. And what this function does is it reads from a socket channel into a 2048 byte buffer, and produces that as a byte vector, which is an S-codec thing that wraps around byte buffer inside of a task, right? So as an effect, it reads from a socket channel. And you'll see it's a little bit different, right? We're using task.async to construct this thing. And what task.async does is it gives us a callback that we will invoke when the task is completed, either with a success or a failure, right? And so we register a completion handler with the async socket channel that, like, whenever our request is completed, whenever our read is satisfied, we're going to call the callback with the result, either a failure or a success. And we can define a write function, which is pretty analogous to this, right? It takes a byte vector, turns it into a byte buffer, and then puts it on the socket channel, registering the completion handler and completing the task appropriately, right? There's no blocking here. There's no sort of suspension of threads or anything like that, right? It's basically what we want in terms of callback threading, but it's wrapped up inside of task, which is this really, we've already said it's like this really monadic, really useful thing. And once it's wrapped up inside of task, we can use it in a really clean way, just like we would use things in our simple lazy program with print lines, right? So here's how we would put it all together, right? We create a socket channel to nothingness, I guess. I don't actually even know why that API is there. Then we read from the channel, and then we parse something that looks like a version. And if it looks like it's the right version, we read again, and we acknowledge the read. And if it's not the right version, we shut down the channel, right? These are the sorts of programs that we write all the time. Probably not quite so naively, but we write them all the time, right? And you see that we didn't have to worry about callbacks, so like the difference between synchronous and asynchronous stuff in here. Like we just sort of sequenced it all together, and it was really clean and elegant, right? So task is basically doing the things we want. But there's a huge trap here, okay? And if you have used task to write a real system, I promise you, you have run into this trap, whether you know it or not. So the trap is here. And the question is, what thread are we on? Does anybody know the answer to this? What thread are we on at this point in the for comprehension? Anyone know? The answer is the NIO event dispatcher thread. Yeah, like that is the right response. What? How did this happen? Why are we on the event dispatcher thread? Don't do that. It's bad. Okay? So this is a trap, and task does this. Like everybody's program that uses task is doing this. It's terrible, right? So this doesn't get said enough, right? Either in blog posts or in talks or anything like that. So I'm literally just going to inject this slide, right? Here's what you do with threads. Okay? You divide your thread usage into 3 categories. Computation, which is CPU-bound stuff, right? Pure computation. Blocking I/O, which is like using these legacy Stone Age frameworks like java.io that block threads and do other horrible things, but you can't do anything about it and you still have to use them. Like blocking I/O, this is a separate class of computation. And then finally, event dispatchers. This is 3 separate categories of thread usage, right? And we're going to allocate a single pool for each of these categories, okay? So the computation pool is going to be work stealing, non-daemon, exactly the number of CPUs in size, right? Modulo, like, you probably don't want a thread pool of 1, okay? So set a min size on it, but just basically exactly the number of CPUs in size. Because this is what's going to give you the most throughput with the least contention on your computation, okay? Blocking I/O has to be an unbounded thread pool. And if you've ever done systems programming, the word unbounded should make you squirm, okay? Because it's really, really dangerous, right? Unbounded things are terrible. They destroy back pressure. You never want to use them. But with blocking I/O, you don't have a choice because you'll run into thread starvation issues if you don't, okay? So you have to have an unbounded thread pool. And then finally, your event dispatchers, right? This should be a very, very, very small pool. This is the only pool you have if you're using Node.js. So this pool should be really, really small. Ideally, like 1 to 4 threads is what people generally find is pretty worthwhile. 1 thread is a totally reasonable default. It should be very, very high priority and daemon. And the high priority thing is really important because like when an event happens on like an async epoll loop or something like that, you want to handle it right the heck now, like really right now. And you want to get off that pool because you're probably going to do some computation with it. So you need to make sure that you move your computation from the event dispatcher pool to the computation pool because working on the event dispatcher pool is bad. It needs to go get more events, right? So this is what you do with threads. In like any system that you want to do at scale, this is how you do it. And Scala Z7 task does not help us, okay? It actually makes things worse because it gives us this function which sounds so promising called fork. And fork sounds like it would do everything we want, but it doesn't work. It's broken. It doesn't handle the use case we need, a use case that is incredibly common, the use case of moving from one pool to another. Fork doesn't do that, and it will just silently not work, and you like end up wondering why your throughput is terrible, and you just assume that it's functional programming, and you go live in a cave, right? So like, the fork is just responsible for all evil. So task, it does these things. It doesn't help us. It encourages really, really dangerous parallelism, which, again, I'm going to show you why this is in a second. But the essence of it boils down to resource management, right? So resource management, it turns out, is kind of an important thing. You don't want to like allocate a resource and then have it disappear and never get released, because that's how you get out of file handle exceptions. So, but task really encourages us to write programs in a way such that resources just float away and we have no control over them. And that's really, really, really bad. So we have to take this problem seriously. So what does task encourage us to do that's so bad, right? How is task encouraging us to do this? Well, it's basically encouraging us with this pair of functions, all right? So task has a couple of concurrency tools, but they're basically built on top of this. You have both and you have race, right? The both function is basically zip on future, where you take two tasks, task of A, task of B, glue them together, and you get a task of pair AB. And then race is a little bit more esoteric. You have a task of A and a task of B, and you run them in parallel, and whichever one wins, you return that result, okay? So that's what race does. And these are kind of the foundation of Scala Z7 tasks concurrency functionality, and it's really, really, really dangerous, right? These functions, as implemented in Scala Z7, are really, really, really bad because you can do things like this, okay? So here's a task that presumably acquires some resource, right? Task of research, because vowels are bad. And we're going to put it together with both with a task that just throws an error instantaneously, right? So the result of both here is going to be the error. And presumably acquire resource is going to get shut down. But what happens if the resource was actually acquired before the error was thrown? Where does that resource go? The answer is into the ether. And hopefully God will deal with it. We can replicate this issue without using errors by having race, right? So acquire resource 1, acquire resource 2. Whichever resource gets acquired first here will win, and the other resource will leak. And we won't be able to do anything about it. We've just completely lost the handle to that resource. So this is bad, right? Like, you can't have resources going away if you want to run your system for months and months or years, right? Like, that's just not an option. So Scala Z7 task, like, it's a step in the right direction, but it's not really all the way there, right? It doesn't provide thread control functionality. It has completely broken concurrency that everybody wants to use because it's there and it makes sense, but it doesn't have resource management, so you just really, really can't do anything with it. And it's really, 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 really slow, which is hilarious because the whole point of this is we want to write all of our program in this thing, but it's slow, so good luck being fast. Like, that's basically the sales pitch for Docker, but like it's not good, right? Performance is important, and Scala Z task just like doesn't get the job done, which is ironic because it's getting the job done in most code bases right now. But like it doesn't get the job done well, right? We can do better, and on top of all of this, it's really, really, really concrete. Okay? There's no abstraction at all. You're using task, and it's exactly task, and it's exactly this task, and there's nothing else you can use. And the whole community just has to agree that we're going to use exactly this task and nothing else. That's very constraining and unfortunate, and it's painted us into this corner over the last 5 years that I want to do something about right now. So task isn't quite there. What other options do we have? Well, we could have continuation T free of function 0, unit A, right? No. This is, so just a quick, like, people who can brag. Like, how many people actually understand this type signature? Okay, cool, really good job, props. I don't understand this type signature. Like, I wrote it, and I don't understand it. Like, this is confusing, and no one actually wants to use this, and also it's slow. But if this is task, it's just, I don't know, it's not going to get the job done. So, a number of frameworks have tried to step forward and fill the gap here, right? So FS2 and Monix are probably the most well-known ones here. And they offer things in their tasks that are really important steps forward, right? They provide resource management. They provide abstraction, right? FS2 kind of gives us an abstraction framework for the first time. And performance, right? The performance of these tasks is significantly better than in Scala Z7. Monix's task in particular is really, really, really fast. But both of them are tied to this larger framework that you might not necessarily want, right? If you use Monix's task, you're using Monix. If you use FS2's task, you're probably using FS2. And while Scala Z and CATS are kind of these frameworks that are like very general and you're probably going to want to use them anyway, Monix and FS2 are kind of a different question, right? If you're not doing streaming, maybe you don't want them. So our goal is to try to find something different here, and we've sort of failed. which is why I started the cats effect project. So cats effect defines I/O, which is 2 fewer characters again. So like, life is good, right? We can write this much more simply with a single hand on an English keyboard. It has all of the constructors that we want: pure, apply, async, raise error. We bike shed it a little bit, but it's basically the same thing as task, and has much simpler internals. Okay. So the implementation, like with the benefit of 5 years of hindsight, right, we were able to take a step back and do things a lot better than Scala IO task did. And there's a lot of room for improvement here as well. Most importantly of all, we provide abstract type classes and laws. Okay? So we define what it means to be an effect. We define what it means to be a monad that manages effects, and we provide a set of laws, which is basically like a TCK, right? A free test suite, which you can use to check, does my random implementation of effectfulness actually work? And it will give you a yes or no. And there's no concurrency at all. Okay? This is probably a little bit surprising, right? Like I said, concurrency and effect systems are really, really important, right? Like, why would I say no concurrency at all? Well, the position of cats effect is basically that concurrency is really hard. It's hard to get right. It's better for cats effect to concentrate on just being a good effect monad, right? Being a good way of controlling effects, a very small composable primitive. And then larger frameworks around us, such as FS2 or Monix, can provide that functionality in a better way than I could. Because that's a hard problem to solve. I don't want to solve it in I/O. So that's basically what cats effect does, right? So it's just a monad for managing effects. And you can find your concurrency somewhere else. And it looks basically like task when you use it in practice, right? This is the program from earlier. All I did was change task delay to I/O. Doesn't it look so much nicer? Everybody's happier now. I'm happier. This is cool, right? And we can do the asynchronous stuff too, right? So here's the async socket channel thing, except you'll notice I've added a line here, which is io.shift, okay? And this shift solves the problem that we had earlier where we were on the wrong thread pool, right? So we come off of the write to channel thing, which is going to be on the NIO event dispatcher thread, and then we shift to the CPU pool, and then we close the socket channel from the CPU pool. Easy peasy, right? This is exactly what we want. It's a very, very straightforward function. And you could define this for task, but task doesn't do that, so I/O defines it for you. So shift allows thread assignment as an effect, thread pool assignment as an effect. It reallocates computation following its sequencing, right? So everything after it goes into the for comprehension is going to be on the pool that you supplied. It is the only thread-related function in cats effect, right? So I said there's no concurrency in cats effect, right? And shift is not concurrency. Shift is just moving things around on thread pools. And originally we didn't have it, but it turned out that we needed it because nearly every real program needs this function, right? Like you literally need this all of the time everywhere. And when we started prototyping things on top of cats effect, we realized that, we actually kind of need this literally everywhere. So we defined it, right? But it's not a primitive. Right? It's not something that's defined as this sort of built-in thing. Users could define it themselves. We just baked it into the library because it's just way easier that way, right? So I'm sort of running out of time, but I want to very quickly get to abstraction, right? Because I've been talking about it all along as like this really important thing. And this, I think, is really cats effect's primary contribution to this space. Cats effect defines what it means to be an effect in a very generic way, and it does it with a system of type classes. So I apologize that the font is a little bit small here, but basically what we have is monad and monad error. These are type classes that are in cats. Monad error is just a monad that you can put errors into, in this case throwable. And then we've got some type classes that cats effect defines. We have sync and lift IO, which we already saw, async, and effect. Each of these type classes is sort of progressively more specific, a more specific type of effect, right? So sync looks like this, okay? You have some type constructor f, and you can define what it means to capture a lazy synchronous effect in this thing. There's no callbacks or anything. We haven't managed async. We haven't managed errors. Well, errors are managed for us, rather. We're just capturing the lazy effect. Async is the same thing, but for callbacks, right? So here's that function that we were using earlier. It kind of captures this weird callback signature that will receive either a result or an error and give us an f of a as a result, right? So this is callback management. And this is async. Every async effect is also a synchronous effect, right? We just define that to be the case. And then finally, we have effect, which is the most constraining one of all. And effect basically defines that your type constructor f can run into an IO in an asynchronous fashion, right? So you can take your type constructor and your effect type and run it into an IO, and that becomes a meaningful thing. So it's relatively easy to be async, right? Like literally all you need is laziness and error handling. Like, I mean, it's really, really easy to define this and be lawful. Async requires callbacks, okay? So this is where you start to become a little bit more constraining, and you really have to work at it. And effect is like, you are literally I/O. Like, you are literally an I/O monad, nothing more or less. And that is a very, very, very constraining type. But each of these types is quite useful. And you can define different things if you're a framework author, depending on which level of abstraction that you need. So critically, though, with these type classes, parametricity isn't enough, right? We can't just look at these type signatures and be absolutely sure that there's only one correct way to implement these functions. So it's very, very easy to build wrong implementations. So what we do is we define a set of laws that constrain the implementations. These are basically, like I said, like a TCK, right? A test suite. Users can rely on lawful behavior. When a user says, I want an async f, they're going to get an f which like matches the laws, unless the implementer was doing something kind of hinky. Implementers can use these laws as a free test suite, right? It's hard to write tests. Use the tests that I wrote for you. That's way easier. And these tests kind of look like this, right? There's actually more of them, but we basically define kind of effectively the things you would expect, right? So suspension of a pure effect is the same thing as pure. If down at the bottom, if we suspend throwing an exception, that should be the same as, raise error. Like all of these things, right? Really, really simple equivalencies. But it turns out that if you do enough of these, you really constrain what it means to be synchronous, and we can rule out a number of things. If you're an implementer, you can run these libraries. So like here is how you would run the sync tests, the laws, against either t eval of throwable, which is the either t monad transformer around the eval monad from cats. And you can test to see if those laws pass, and you just get like a bunch of test output, right? There's actually quite a bit more than this, but it doesn't fit on a slide. So these laws, they prevent invalid instances. Invalid instances like, say, future. So we said right at the beginning that like future doesn't actually work, right? It doesn't propagate errors. It doesn't manage laziness correctly. It's eager. It doesn't resequence. The laws catch all of these things automatically. We don't even have to think about it. We just try to define an instance, and then it breaks, and we're like, oh, okay, so it doesn't work. There's other instances which are sort of surprising that don't work, right? Kleisli. Kleisli is the monad reader transformer, right? And it turns out that you cannot define a sync or an async or an effect or any of those things for Kleisli of some sync or async because you don't have stack safety, right? And we defined right at the beginning that like stack safety was really important. We're not going to let you be an effect type if you don't manage the stack for us, so that the laws will capture all of this. Frameworks can rely on these laws and these abstractions to build things that are generic, that don't require my specific implementation of I/O, that they work with like everything else, right? So like FS2, for example, can use my I/O, but because it's built against these abstractions, it can also use Monix's task or the Scala Z8 I/O that you're going to hear about in a little bit. Like all of these things are possible because of the abstractions, and it frees us up in a way that we've never been freed before. So FS2 does this, HTTP4S, Doobie. Like there's several other frameworks that are now using these abstractions. And even though it kind of ties you to Cats in a sense, like Cats' notion of things is pretty compatible with Scala Z. So it's not really that constraining in the end. And this framework, these laws are very, very, very valuable. So you're not forced into this. So in conclusion, and hopefully we will be left with like a little bit of time for questions, effects are scary. Effects are scary in every language. It doesn't matter what you're doing. The I/O monad helps you manage them. And especially if we can be generic about it and define what it means abstractly to be an I/O, it can be really, really, really powerful. All of these options that we had before today were bad, right? Like they really just didn't get the job done. They were really smart in their day, but they are quite old, right? Scala Z7 task is like 5 or 6 years old, and we've learned a lot since then. I don't know. Hopefully this was all interesting. That's all I've got. Does anybody have questions? Yes?
Is there like a reason that throwable is completely baked into the type class
Yeah, so repeating the question, the question was why is throwable baked into it, like sort of hard-coded, right? Why don't we have a more generic error type? And the answer is that throwable is the exception type on the JVM, right? It's not even just Java, like Scala, Clojure, JRuby. Like it doesn't matter what code you're delegating to, they have to put exceptions into this type because that's how the JVM is written. So if you want to manage effects that are not exceptions, you should use an either T or a validation, right? Basically, the position of cat's effect is that, like, if you're an effect type, you have to handle exceptions. You don't have any other options. You have to handle exceptions, and those exceptions are going to be of type throwable. We do make sure, though, that we're not catching things like out-of-memory exceptions or stuff like that, because out-of-memory error, I don't know if you know this, but if you catch out-of-memory error and then recover it and then keep going, your JVM is actually in a completely undefined state and can, like, things like math can stop working. Don't do that, right? We don't do that, okay? We're very careful not to do that. That's just going to crash your JVM. Anyone else? I think we're done? Okay. Thank you very, very much.